So this is the agenda of this whole session. We'll quickly go through. Actually, we'll try to understand what is big data, basically, and then what decides what is big data, and if there are any types, and then in the first place, why we needed this big data, and uh, a sample case. We're going to take up a sample case, how some data could be a big data and how we can actually solve it, how they came up with this solution. And at the end, we're going to see a couple of those use cases. So that's the basic question. What is the big data? So what is your idea? Yes, that is kind of a technical definition. So what do you think? Any ideas? So big data is a huge data. Yeah, that's obvious. It is big. And is the size itself defines the big data? And if size defines the big data, what we can actually comfortably call a big data? But the technical term we see, if you go through it, big data is a broad term for data sets large or complex. Traditional data processing applications are inadequate, and challenges include analysis, capture data, curation, search, sharing, storage, visualization, and information privacy. That's a lot into one paragraph. But we'll see what we can actually call a big data. Yes. So if we go back a little, and during 90s, only that was kind of we were having this IT startups. Only IT companies were generating the data. Only whoever working in there were generating the data, and people outside, they're not using much data, and most of them not using data at all. And we are talking about the digital data, of course. But things changed slowly with the advent of social networking sites and e-commerce. Things changed drastically. So even normal users started generating data. And this was a game changer, mobile phones and the smartphones. And they were the biggest reason of the most of the data generated recently. And they say 80% of the data in this world is generated in the last 2 years. So that's a lot of data being generated because of mostly smartphones. So even these stats are a little old, but still that's really big. So Facebook uses nearly doing 2.5 million pieces of content, and Twitter 300,000 times. This everything 220,000 new photos. These are for every minute. Every minute there are 72 hours of new video content added to YouTube. But these are a little old. If you have the latest one, even that would be even bigger. So there are more stats. But we already aware of these things, but there are more stars where the data is generating from. So earlier times only mostly working in IT were generating data, but things are changing slowly with IoT and healthcare. It mostly about sensors. Sensors are generating data from healthcare, from say Walmart, and financial sector, and almost everything, even driverless cars. And there is not a field that won't be touched by this. That is, where the data is not generated from. So almost every field they're using information technology, and they are generating data. So the question is, what we can call a data, a big data. Comfortably. So volume is obvious one. So the volume should be really big. but how big? See, once upon a time, when we were using that floppy disks, they used to be 1.44 MB, somewhere around. That was really small, and at that time, even the desktops hard disks were 20 gigabyte. And at the time, if someone had to process, say, 100 GB, that was like a big data when we were using floppy disks. And nowadays, everyone is having a 500 GB laptop or even a 1 TB laptop. So can we call 100 GB or 200 GB big data? No, uh, because almost everyone can store it. And what if we can call terabyte or 2 terabyte a big data, or a 10 terabyte a big data? 10 terabyte a big data can be called if it is a startup company. But if it is for Google or Facebook, would that be a really big data? No, might not be. Yeah, that data might not be really big for them. So it is also a bit relative. We are still volume is obvious, but it's still relative to the time and their situation. So technically, it all comes down to whether your existing system would be able to handle the data or not. Would it be able to store it and process it? But volume alone will decide the big data. No, there are more. One more is velocity. So the velocity is at what speed the data is generated or the data is coming into the organization. So think of a small startup company, and they started with say 1 terabyte of data. Say every couple of years, I mean they needed 1 extra terabyte of data processing power. So will they be having a big data problem? No. I mean that might not. 2 years is a long time, so they can comfortably add new hardware and upgrade. Yes, they can manage it. But if 1 terabyte of data coming in every month or even every week, so at the moment all they got is 1 terabyte. At the moment they don't have a big data problem. But can we still say if there is a 1 terabyte of data coming in every week, so they are having a big data problem because of the velocity? And the third one is variety, but mostly the volume and velocity will decide whether it is a big data or not. But the third characteristics they're talking about is the variety. So nowadays things have changed. We are moving away from these traditional databases. So there is loads of unstructured data. People are posting pictures, videos, and a lot of content in the form of text. So all these are unstructured data. Traditional database systems, they are built to process mostly structured data. So handling unstructured data is not possible using the traditional database systems. Let's say that's the volume we are talking about. But it depends on that. It's relative to the time and the situation and the velocity. And also, I mean, people who are doing a sentiment analysis, going on to social networking sites, there's a lot of data they would be collecting, and the velocity with which it would be coming in is also, I mean, too high. So that e-promotions, healthcare monitoring is, I mean, the wearables and even the hospitals, they are using a lot of these sensors, and they are going to use in future almost on every patient or even a normal person. So this data is really important, and that should be processed within the time before it could be too late for some patient. So the velocity is important in places like that. And the variety. Variety is, I mean, traditionally it was all in tables, but it was nowadays it's loads of text, pure text dumping in PDFs or text files or in HTML, and images and audios. When I say images, it's not about storing the image into a table, but someone can get into that image and search whether there is a person in that image or not. Something like there is a CCTV camera, and normally no one enters after some 6 o'clock in the evening. But nowadays they are coming up a new intelligent cameras. They can actually, give an alert message, send a message to the police or even, the owners. There a person entered in, even someone without someone actually sitting in front of the screen and watching that CCTV camera recordings. Continuously. That is possible nowadays. So even the cameras are reading the number plates of the cars and sending the fines to the people. So this is becoming more possible. But to get into an image or a video and find something is it's not a structured data. It's a really difficult thing. So that is not possible using that traditional databases. But this because of this unstructured data or semi-structured data. So we are running out of, they are running out of options. So they needed a new system which could actually store huge amounts of data and at the same time process it and also handle not only structured data but semi-structured and unstructured. Let's skip through some of these. Yes, that's the one I was talking about. That's the types of data we are, having nowadays coming in. That's a challenge processing semi-structured and unstructured. So structured data, all the systems are so developed and they can readily process the data, but there's a challenge with incoming unstructured and semi-structured data. So yeah, that's the three ways we were talking about: volume, velocity, and variety. And they are adding, a few more ways. Velocity, because the data has to be consistent. So if it is not having, if it is inconsistent, you just can't consider it. It is like a huge data, and you're going to dig into it and find the data that is valuable for the organization or for us. And if you are doing that, it has to be consistent. That's why they added this velocity, a new way. So what's wrong with these traditional databases? So we have mentioned, few of them. So because RDBMS, traditional database systems are developed, process structured data, mostly using that SQL. But however, the volumes of data is changing drastically. At the same time, the velocity with which it is coming in. So the traditional database systems, they are not built for handling this huge amounts of data because we needed a better hardware, custom built, which could be really expensive if you want to scale the size, even if you're talking about the storage, if you keep that unstructured, semi-structured aside. It is really difficult to store this data on this traditional database systems, the kind of enterprise hardware we buy in the market. And for a really bigger data sets, we probably won't even able to buy the hardware for it. We may have to custom made order, and that would be really expensive. So the data size has increased. Yes, it is nowadays running into petabytes. So RDBMS is it's really difficult to store and process it. It is going to take hours and days, even if you try, doing so, adding that enterprise level hardware and software. To address RDBMS, yes, we need a more central processing unit. So we can probably buy extra hard disks, but processing power is a little difficult. Replacing the CPU with the higher processing power, that's going to cost a lot. And also that majority of the data nowadays are coming in are semi-structured, unstructured, and then we needed a solution to actually process it. Say data from CCTV cameras, for example. So the second problem related to unstructured data is outside the purview of RDBMS, and we were talking about. They are designed and structured to accommodate only structured data, not, I mean, all kinds of data. And the velocity, and if you wanted the hardware for it, it's going to be really expensive. So there are, I mean, new technologies. I mean, they came up with solutions. One of them was Teradata, and it is a parallel RDBMS. I mean, they started, I mean, processing this data parallelly, which would be really quick. But there is a problem with the scalability, and also still scalability is expensive, and the licensing is expensive. At the same time, uh, if you want to process the semi-structured and structured, they're still not built for it. And when they were building it, I mean, they had some kind of huge data in their mind, but not the kind of data size of data we are experiencing nowadays. So that Hadoop comes in, but we're going to talk this Hadoop part a little later. So before we go any further, let me differentiate these two words a little clearly, that big data and Hadoop. So what is big data and what is Hadoop? So here I just listed out these are the big data challenges. So big data is actually the real big data, but here when we say big data, we actually mean the problems that comes with the big data. So we can actually say big data is a problem with the big data, and Hadoop is a solution. So when we are talking about saying big data, we are not just saying that it is a big data, but we are actually indirectly meaning to the kind of challenges that comes with the big data. So these are the challenges comes with the big data. So we are, I mean, having this big data generated out there. So what are the challenges that are coming with the big data? The first one is storage. So when it is so huge, we can't be storing into, I mean, normal single hard disks, or they have to be connected in series. And then, I mean, it should be in a distributed environment, of course. And then processing. Processing also is a huge issue, and we needed higher processing power. And also data loss, we need to have a good recovery strategy, because if you are handling really big data, there's probability would be more that we would be losing some data. And also the cost. The cost of, I mean, finding solutions to all of these things, for the storage, the hardware, and the processing power, the hardware, and the data loss recovery kind of the softwares, and even the extra hardware we need if you want to have multiple hardwares. So these are the challenges that come with the big data. And as I was saying, big data is a problem, and Hadoop is the solution. So let's take a simple example, see how we can actually come across a big data problem, and how this Hadoop, I mean, comes in to rescue as a solution to this problem. So say if you're working in as a data analyst or a big data developer, and then if you're asked to analyze a stocks data, say if you are given a stocks data set, stocks data set which covers, say, from past 10 years of data of a stock exchange. Say if it is just 1 terabyte, and if you are asked to find the maximum closing price for each stock, yes, on each day, or each month, or each year. So we have to dig through last 10 years of some stock exchange data and find that maximum closing price on each stock on each day, or if we are doing this on average for each stock symbol. So with the normal systems, the first thing what we could be doing is we bring in this 1 terabyte, and what we could do is, if our hard disk only say 50 gigabytes of space left, what we can do, we can go to the administrator, network administrator or system administrator, ask him to copy into a storage server, and then we'll ask him to give us permissions and the address, how we can access it, and then come back to our system, start writing the code to find the maximum closing price for each stock symbol. And then when you start actually executing the program, what's going to happen? So the 1 terabyte of data is sitting somewhere on a storage server, and we have to read it over the network. The first thing is the reading speed of a hard disk. So here it is saying 122 MB, but normally it could be 30 or 40 MB, but say the best case, we take the best case, 122 MB. And to read 1 terabyte of data, so that's going to take somewhere around 2.5 hours. And after reading it, it is going to hold that into the buffer and start processing using our program when we start executing our program. So the program computation time. So we also have to take the consideration of program computation time. Read it and execute the program. Program execution on 1 terabyte of data, that might take more than 60 minutes. So 2.5 and say 3.5, nearly 4 hours. And we have to also take into the consideration of network bandwidth, because we are not reading it from our local hard disk. We are reading it over the network. So that could add another 30 minutes or 1 hour. So can you think of it? I mean, executing just one program, that could go up to 5 hours. And if that's for just 1 terabyte, if it is 10 terabytes, that could potentially go up to 50 or 60 hours just to execute it. And if they come back and say, make the changes and give me the result. And making changes is little easier, because we already wrote the program and making few changes to what they asked for. But if you want to execute the same program, how long it's going to take if it is a 10 terabyte? So that should be another 50 or 60 hours. And if it breaks in the halfway, and we'll have to do it again, redo it again. So it's technically taking days, even with the few terabytes of data with the traditional ones. But this is the one course we are looking at is mostly batch processing. The big data is mostly batch processing. There is stream. We will also see one tool we use for it, analyzing the Twitter data. But at the moment, what they are using is mostly batch processing. So already stored data, they're going to dump into your network, and you're going to do it. We're going to actually read and analyze and generate the reports what they are looking for. But this was the problem. So if you understood this problem, so what could be the solution? So we are looking at only 1 terabyte of data, and then we are reading it over the network, and we don't have enough space on our local computer, so we got it stored somewhere on a different server, and we have to read it over the network and execute the program, and we have to take into consideration the network bandwidth delay. Yes, Meenakshi. Yes, let me go ahead. And we have to, I can't hear. Did you try to say something? I'm sorry. Did I miss something? Yeah, let's finish this small case, and let's go back to if there are any questions. So this is a problem we are having at the moment. Reading 1 terabyte of data, it's like a batch processing over the network, and it is taking potentially 5 to 6 hours. And if it is 10 terabyte, that could be 50 or 60 hours. So how can we bring down this execution time? So the kind of solution, even this is very similar to how they came up with the solution. So this is one technique. What if I could be able to divide this 1 terabyte into 100 equal pieces and process them on 100 different CPUs, and if we can call them nodes, and the result we're going to merge them on using a different node and give the result. So if we divide them by 100, the total time, and total time to read, that could come down to, I mean, around somewhere around 2 minutes just to read, and computation time could come down to less than a minute. So if we divide by 100 with the earlier starts, so this could actually drastically bring down the execution time. It's less than 3 minutes. Does it make sense? But here we need a cluster of computers, but not really kind of high-end or custom-made. The normal ones, I mean, whatever they are existing in a network. But this is the idea behind it. This is the idea behind it. If divide the data set into a number of smaller pieces and process it parallelly on different nodes, say 100 parallel computers, and the output results, and group them together, merge them together, and give that final output we are looking for. That makes sense. So that's, I mean, the whole idea is, I mean, sometimes bringing the storage closer to the processing. Normally, if we are dealing with this huge, I mean, big data, the problem is reading the data which is sitting somewhere else. Or you can think of it in earlier situation. So we are having a 1 terabyte of data. Say in there, if we have 10 terabyte of data, and we are writing the same program to find that closing stock price for each stock symbol. So the program actually we write how big it could be, somewhere around 1 or 2 megabytes. If it is just 2 megabytes, or it could go up to 4 or 5, but we'll say average if it is a small program, say 2 megabytes. The program is 2 megabytes and the data is 10 terabytes. And we are trying to read this 10 terabytes over the network. So instead of bringing this 10 terabytes over the networks to the program, why can't we just take this program, whatever we actually did, this 2 megabyte, to where the data is existing and execute it over there. If we could achieve this, and we could bring down all the time. And also, I mean, we split the data into say 100 equal parts and run this program parallelly on different nodes, 100 nodes, and process it. We could drastically bring it down. So this is the whole idea. Yes. So this is the whole idea behind it. Bringing these two things closer, the storage and the processing. Bring them closer, and so that there won't be bandwidth delay, and you don't have to read that huge amounts of data over the network. And also, I mean, you're going to split the data set and process it parallelly. So this brings down the execution time drastically. So this is the idea behind this Hadoop. So as I was saying, big data is the problem, the actual challenge, the actual problem. Then Hadoop is the solution. So how this forms a good solution for big data problem is that it supports huge value. So it got, one part as HDFS, which is the storage part. The first thing, if we, go ahead and we're going to see that HDFS first thing, and then MapReduce is the processing part. There are two main core parts of this Hadoop framework. So Hadoop is a software framework built using Java, and this is specifically to process big data set, parallelly on a distributed systems. So it supports huge volumes, and there is storage efficiency, and also good data recovery solution inbuilt in it in that framework. So by default, if we store any data onto HDFS, the replication factor, what we call, is 3. So data is divided into blocks, and each block is stored on different nodes 3 times. So 3 copies of them will be stored, and the biggest advantage is this horizontal scaling. So instead of vertical scaling the traditional database systems, you can actually scale it horizontally. So you can add number of nodes, any number of nodes you want into the distributed system, and it's also cost effective because you're not actually using high-end enterprise hardware. It is the normal hardware, servers, whatever you buy in the market. And it's easy for programmers and non-programmers. This bit is, you will only get a clear picture once we go ahead and learn 3 or 4 tools out of it, when we learn Peak and Hive. So those tools were developed for non-programmers, and MapReduce is for programmers. So the question is it a replacement for the RDBMS or the existing database system? The answer is actually no. The answer is actually no, because if you try to run, it is mostly for batch processing, not like a query execution. It's not really efficient for query execution. But there are tools you can, the NoSQL part, you can actually use it for query execution. But initially, it is mostly for batch processing. Whatever data is already stored, and you can dig into the data and find the valuable information, bring out the valuable information out of it. So is it really replacement for RDBMS? No, because it takes time. If it is a smaller data set, RDBMS it works excellent. It's only if it is too big, so that the traditional systems won't be able to handle it, then only, yes, one normally goes for the big data or Hadoop. So it is like, if you take an example as if someone has to dig a hole in the ground, and say if it takes 4 days for one person to do it, and if you want to bring it down to say 2 days, and what we can do, can get 2 people, can hire 2 people to do that. What if you want to bring it down to just 1 day? We can hire 4 people. But if it is a really smaller data set or a small task, and if you want to use the big data, it would be like, digging the small hole on the ground, employing like 50 or 60 people. They won't be even able to stand around the hole. So it only works with, Hadoop only works with, is good with huge data sets. If it is a really small one, if we are trying to, run a simple query using Hive, it is going to take time. So when it takes time just to load class libraries of the framework and start executing. It takes 30 seconds to 1 minute already. If it is even bigger, it is going to go up to 2 minutes, 1.5 to 2 minutes. So when the user needs, quick answers, like a traditional RDBMS SQL queries. So for smaller data sets, it's still good. RDBMS is still good. Only if it is, too big, way too big, the traditional won't be able to handle it, then only it is good. So it is not a replacement for RDBMS. So this is the brief history of Hadoop. So this was the guy, Doug Cutting, who was working with the Yahoo, and he was trying to, develop a framework which can actually process the huge data. What he was trying to do was index all the web pages into one database, and he was facing a lot of challenges regarding the storage and processing. And that sounds exactly like what Google were doing actually. So Google company has succeeded doing it, and they published a paper, GFS, Google File System, and the published paper actually gave solution to his problem, the dog cutting, and he just adopted it. And after that, uh, even one more paper published, and out of it he picked up this MapReduce, and he actually developed this Hadoop using that. And then he went back to Yahoo, and he also improved it, but they kept it as open source framework. So if you want to go through it, that's a small history. So at Yahoo they also developed Pig for non-programmers, and at Facebook they developed Hive. So yeah, that's the timeline. And so there are distributions. We can look at them at a later time, the cloud era. So let's go ahead and see a couple of use cases and wrap up this session. So if there are use cases out there, yes, there are a lot, but we're gonna see just a couple. I don't know whether, I don't think you would be able to hear it. Let's see. That was that Obama swearing-in ceremony. So the question is, so what Obama swearing-in got to do with the big data? So if you might have come across, few news articles, you might have, seen that Obama election campaign used big data. So how are they using it? Actually, it helped him to come into the power, to become the president. But how it was helping him? They say he had 80 member team or maybe 100-member team just to do this work, sitting in their party office or somewhere else. They had a special team for it, and they're working throughout the campaign. So the one thing they were doing was they were going through these social networking sites and even blogs, and they're collecting all the content from there, and it's kind of a sentimental analysis, but they're just doing, you can think of it, if he is going for the campaign to one state tomorrow, say Texas, and these guys already collected all the data from this from the Twitter and Facebook, other popular social media, and a few popular blogs. So they read all the content from say last 1 year or 2 years, and then they got all this huge text lying down, there. And what they could be doing is, this is the kind of a first program we would be doing when we go ahead, is that word count. So read through all these sentences, collected from all the social media and other websites, and find out how many number of times each word repeated, and then sort them, depending on the number of times repeated, highest being that at the top, so descending. Then they're gonna filter these things a bit more, filtering out all these is that it simple words, and then the top 10 or 20 words give them actually what people were talking about the most. If something looks like an issue, yes. And when he actually goes to Texas in his speech, he's going to actually touch these top 5 things or 10 things in his speech. And if they find out, okay, most of the people are talking about these are the top 10 issues. So let's talk about top 5, and if he finds time, he's going to top 10, and he's going to actually his team is going to come up with the solutions or his ideas of solutions, and they're going to include that in his speech, and he's going to immediately connect with people. Looks like, okay, this guy knows what they are facing. That's just one of, I mean, so many use cases out there. Just look at one more, and we'll wrap it up. You guys, can you hear the volume? I don't think so, because that's a system volume. So let's see. So yes, I was looking at looking for that one sentence. So if any one of you, I mean, came across this incident recently happened a few months back. So a passenger was dragged out of United Airlines, and the flight was overbooked. Surprisingly, yes. Even a normal bus in here in India, they are not overbooking it. Even the government buses. How could this airlines is overbooked? Yes, this is probably one of the fields they adopted this big data at the earliest times. So the airlines were actually bleeding losses. Most of them because the competition was really high. I mean, there are too many out there. And it is becoming really difficult to actually optimize the scheduling the flights. It's like if one route, I mean, their main problems were, I mean, something like this. If they got say 10 flights, and one is for say London for mostly business and travel, and they are sending 7 of them regularly to London, and another 3 for some holiday destination. So at one particular part of the year, and this changes if they're still doing the same thing, and 7 flights to London, and they are going there off empty, even only 30, 40% of occupancy. So they are paying the staff the same money, and they are using the same fuel, and they are paying that airport charges the same way, but flight occupancy was just 30 or 40%. But for the holiday destination to which they are running only 3 flights, and flights are fully booked, and even people are still waiting for other flights, other services, and they are left out. People are left out. They couldn't find a flight to go there. So one solution is, I mean, if you think of it manually, so in that holiday time, we can switch these 2 things. I mean, send 3 or 4 to London, and then another 5 or 6 to holiday destination, and that could balance it and optimizes it. So when they are, I mean, running hundreds of flights to say 50 or 100 countries, I mean, so many number of flights every day, how to schedule flights for next 6 months or next 1 year, so that the profits would be maximized and the losses are minimized. So that's where, I mean, they are trying to use this big data. So they are dumping all this data from last 10, 15 years to a big data company, and asking them to actually, yes, dig it and find, I mean, give me the best schedule so that profits would be maximum, or losses would be minimum, and schedule the flights for next 6 months. So that's a challenge. And the big data they are not only using to schedule the flights for next 6 months, but at the same time they also found that for every 100 people, say 2 people are missing their flights. So they started issuing instead of 100 tickets, they started issuing 1 or 2 tickets. So they are making maximum money. But what if an extra customer turns up? So one at first customer turns up. So I mean they are using different business tactics like offering him half the price of the ticket to catch the next flight, or full refund of the flight ticket. If someone, I mean, they're gonna offer it to all the people on the flight, so someone would take it who are not in urgency. But on that unfortunate day, so no one took the offer, and they were running late. They had to drag one innocent-looking customer out, and that, I mean, that meant like disaster for their business actually. I mean, the technology has two edges, so that was a negative side, but still, so this is how this one field is using big data. So this is just a picture, last one. So Hadron Collider, if you might have heard it, somewhere in underground near border of Germany and Switzerland and France, somewhere in the mountains. So this Hadron Collider is actually generating 1 petabyte of data every second. That's kind of unbelievable. And they can't actually, this is mostly from sensors, they can't actually keep all the data because it's not practical. So they are trying to only, I mean, capture the most important data and leaving the rest. Yes. So if you look further in near future, so someone came up with this, someone coined this sentence. So data is the new oil. So the world's most valuable resource is not oil anymore, and they are calling it the data. Because I mean, something could turn the tables around. Probably if that Kingfisher Vijay Mallya would have used it extensively before he actually invested in airlines so much, probably I mean he wouldn't have, I mean, fled to UK. He would have still be running his own businesses. So this could be, I mean, a game changer. This could turn the tables around in businesses, and yes, that's why they are calling it the data is a new oil, and that's from Economist magazine. Officially, I mean, they declared that world's most valuable resource is not the oil anymore; it's the data. If someone would be able to actually dig into the data the company has been collecting over the years and find that valuable information out of it, so that actually their profits could be maximized. But I just had an issue with that data is a new oil because the analogy is not so perfect. Because the oil is a rare resource, but data is everywhere. Because of the Internet of Things, when it is implemented in a big way, so almost not only people, every other gadget would start generating data. Your TV, a refrigerator, washing machine, think of anything, they would start generating data. For example, nowadays they are already testing the driverless cars. Every car would be generating data, and every future robot would be generating lots of data. And every patient, not just a patient, probably every person on this planet would be, I mean, wearing those wearables for health purpose and would be generating data. So that sensor data of every human being would be probably uploaded onto the cloud, and then they would be running this analytics on the data and finding the patterns of the diseases and warning them even before something happens to them. So that's why I didn't find it what is the perfect analogy, because data is everywhere. It is going to be everywhere in near future, but oil is a rare resource. But where it actually matches is this abundant of data. So oil is not abundant, but data is abundant. In this abundant of data, if you could actually dig deep and extract the one valuable data, the only valuable data out of it, I mean, that could be the real oil. So Andrew said we need to find it, extract it, refine it, distribute it. Yes, it works that way. Yes, thanks a lot. And probably you might have seen that on the website, or if you speak to Kranti. So these are the emails to reach him. And let's say if you have any questions, yes, please go ahead. We'll wait another 5 minutes and we'll take a leave. Uh, yes, Minax, I can't. Can you type that in? I'm sorry. So how many hours of training? So this could go, I mean, somewhere around 24 hours. It could go up to 24 hours, but uh, it might go a little over that 24 hours. So normally we're planning what are the tools we are covering. So we are covering this HDFS, MapReduce, Pig, Hive, and HBase. So there's a list on the website. If you could go to that KKM trainment, yes. This is a bit elaborated list out there. All right, need Java knowledge. Yes, allowed to say yes for the MapReduce part. As I was saying earlier, if you remember, it is for programmers and non-programmers. So for programmers, it is MapReduce. So if you are not really familiar with Java, and you may struggle a little bit with when we do that MapReduce part. But the Pig and Hive are for non-programmers. Pig is a scripting language. It's called Pig Latin, and Hive is very similar to SQL queries. So it is almost like SQL queries. Select a star from table and everything else. So the Java knowledge is needed only for that MapReduce part. And why outside they're not using MapReduce a lot, but why they're still asking for it is, it's like the whole framework is built upon Java, and the class libraries are in Java, and where we actually code, we can write our own class libraries if we need it. That's one place, but having this in most of the class libraries added nowadays, probably you wouldn't even need that. Is there any online book? Yeah, there are a few PDFs I downloaded, but I won't really recommend you get into the book because it's really difficult to get out. Yes, I was sharing some material. Yes, we can share some material. There are some few PDFs. But while if you, go ahead, with us, I won't recommend you to actually get into the book initially. So once we actually do the class and you do some hands-on and try things, fail, try things and do, and then go back when you get that better idea, then go back and try the book for a better knowledge, to fill up the gaps in the knowledge. But initially, I won't really recommend to get into a book. But I can share those few PDFs. Yes. There will be hands-on? Yes, there are a few use cases or proofs of concepts, what you may call it. So I got few. One with working with the stocks dataset, and one is, there is a songs dataset, the bigger ones, but we don't really use the songs dataset. It is probably in GBs, 500 GB. 3 to 500 GB, but we don't use the actual dataset, sub dataset, but we'll do hands-on. Yes. Yes, for all the tools we do, but that HBase is the kind of last one. We do hands-on, but we're not going to do a bigger use cases because HBase is just like an introduction because it itself forms as another course. So that at the end, that would be more like introducing the tools, but more focus would be on these things I was talking about: map, reduce, peak, and high. Where you spend most of the time. Yes, yes, I've been working. I mean, earlier I was C# developer .NET, but the moment, yes, started working from last 1.5 year. It's more than 1.5 years. Yes. All right. So if there is any more questions or anything, you can write to Kranti using that yeah, two emails. You can call him if you already spoke to him.